Hi, everybody. Welcome to Lecture 13 of Electrical Engineering 331. This lecture will cover no new material. It's just a review of some of the material that we did earlier in the course. And this is certainly not a comprehensive review. It doesn't include every possible thing that could be on the midterm exam, but I think that it is a worthwhile review. So I've done here actually 6 example problems, and so we'll look at these and see what we can do. So for the first example problem, we are asked to find the energy and average power of this particular signal right here. And so I will begin by reminding you that the definition of the energy is this, is the limit as t goes to infinity of the integral from negative t to t of the magnitude squared of x of t dt. And so for this particular x of t, we notice that this function is equal to 0 if t is less than 0, and it's also equal to 0 if t is greater than 2. But for t between 0 and 1, it's equal to 1. And the only tricky part is finding the expression for x when t is between 1 and 2, is this portion right here. And the correct expression for it is 2 minus t. You can see that that agrees because when t is equal to 1, we get 2 minus 1, which is 1. And sure enough, the point 1, 1 is the beginning of that sloped region. And on the other hand, when t is equal to 2, we have 2 minus 2, which is 0. And sure enough, 2, 0 is the end of that sloped region. So this looks like, right here, the correct expression for x of t. And then, since that is the expression for x of t, this integral just becomes, all we have to do is integrate from 0 to 2. That's the only region over which this function is non-zero, is between t equals 0 and t equals 2. And since the function has a different expression over the different parts of that domain, we break the integral up. From 0 to 1, x is just equal to 1, and so we square that, and we get 1 squared dt. And on the other hand, between t equals 1 and t equals 2, x of t is equal to 2 minus t, so again, we will square that and integrate. And so when we integrate, of course, 1 squared is 1, and the integral of 1 dt is t. We're evaluating that from 0 to 1. Here is just a little more complicated. This almost has the form u to the n du, but we need a negative sign on the inside, and so that gives us also a negative sign on the outside. And then once we've done that, it does have the form u to the n du. And so the integral, of course, is 1 over n plus 1. So that's 1 over 2 plus 1, which is 1/3. U to the n plus 1, so 2 minus t cubed. And we're integrating that from 1 to 2. So this first term just becomes 1 minus 0. And then for the rest of it, we have minus 1/3 coming down. And when we evaluate at the upper limit, we get 2 minus 2 cubed, which is 0 cubed. And at the lower limit, we will get 2 minus 1, which is 1 cubed. And so this ends up, of course, 1 minus 0 is 1. The minus 1/3 comes over here. And 0 cubed minus 1 cubed is minus 1. So we have 1 plus 1/3, which is 4/3. So this is an energy signal. The energy that we obtained is a finite number, so it's an energy signal, and that tells us that the average power is equal to 0. And so now we go to example 2, 13.2. Find the energy and average power of this signal. And it says x of t is equal to sine t times the quantity u of t minus u of t minus 2 pi. So what that means then is that For t is less than 0, this is equal to 0, and for t greater than 2 pi, it's equal to 0. But between 0 and 2 pi, we have this sine function, sine t. So this means then that the energy of this is going to be equal to the integral from 0 to 2 pi of this squared. So we get sine squared t dt. Now, in case you have forgotten how to integrate sine squared t, I did a little bit of work over here on the side. I think we've actually talked about this once in this course already, and so this is just a second time. But what I've done over here is just use the cosine of a sum formula, and I then evaluated that for beta equals alpha. So if beta is equal to alpha, this becomes cosine of alpha plus alpha, or cosine of 2 alpha, which would give us this. And then you can follow down from there. I encourage you to take a look at this, and if there are any questions, let me know. But this is just plain old trigonometry here. I'm just turning the crank on some trigonometry, and we end up getting cosine squared alpha is 1 plus cosine of 2 alpha over 2. And then by turning the crank on some trigonometry, a little more trigonometry, we get that sine squared alpha is 1 minus cosine of 2 alpha over 2. So we can, for this sine squared t, according to this formula right here, we can substitute 1 minus cosine 2t over 2. So that's what we will do. And then we can break this integral up into two integrals. We have a 1/2 integral from 0 to 2 pi of 1 dt minus 1/2 again, integral from 0 to 2 pi of cosine 2t dt. And so the integral of 1 dt is just t, and we're integrating that from 0 to 2 pi. And then the integral of cosine of 2t, well, we need a 2 on the inside and bring out a 1/2, so we'll get minus 1/4. And then the integral of from 0 to 2 pi of cosine 2t 2 dt will be sine of 2t. And that's evaluated from 0 to 2 pi. And so we get over here, the 1/2 comes down, and t evaluated from 0 to 2 pi is 2 pi minus 0. And then minus 1/4 comes down, and sine of 2 times 2 pi is sine of 4 pi, which is 0, minus sine of 2 times 0, which is sine of 0, which is 0. So this term goes away. It doesn't contribute at all. And we just are left with 1/2 times 2 pi, which is pi. So once again, the energy of this signal is a finite number. And so therefore this is an energy signal, and since the energy is finite, the average power is 0. Now let's look at example 13.3. Very similar function here, except that now we have sine t over all of time. It never does get truncated. This is just x of t equals sine t for all t. So you see in the graph we have a dot 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 here and a dot 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 here to show that this function goes on and on forever in both directions as sine t. Now, because of that, that means that the magnitude squared of this function does not go to 0 as t goes to plus and minus infinity. And since that is the case, e goes to infinity here. So this is not an energy signal. E goes to infinity. So now let's try to calculate the average power. And remember that the calculation of the average power becomes a little bit easier when it's a periodic function. And this is a periodic function in this case. In the case of a periodic signal, the average power is just 1 over t0, which is the fundamental period, times the integral. And your book says from negative t naught over 2 to t naught over 2 of the magnitude squared of x of t dt. But the truth is you don't have to integrate from minus t naught over 2 to t naught over 2. You could integrate from minus t naught over 4 to 3/4 t naught, or from 0 to t naught. You just have to integrate over one fundamental period. That's all you need to do. And so that's what I'm going to do here, is I'm going to integrate from 0 to t naught, because that's exactly one fundamental period. And so when I do that, for this function, sine t, the fundamental period is 2 pi. So this becomes 1 over 2 pi times the integral from 0 to 2 pi of sine squared t dt. But that is exactly the same integral that we had above, and we found there that integral was equal to pi. So we have 1 over 2 pi times pi, which is 1/2. So the average power for this signal is 1/2. And that means that since the average power did turn out to be a finite number, this is a power signal. Now let's look at example 13.4. We did a few problems like that. We're changing gears here, shifting gears, but we did a couple of problems like this before, and I just want to refresh these in your mind. Suppose that x of t is equal to 2 sine of 6 pi t minus 3 cosine of 8 pi t. Now, I'm saying if this is periodic, find a period. So I'm not even claiming initially that this is necessarily periodic. But if it is periodic, if it's not periodic, you just say not periodic. But if it is periodic, then I want you to find a period. Okay, so let's see how this would go. We know from our previous work that 2 sine of 6 pi t, this first term, is periodic with period into pi over this 6 pi. And when we write that down, then that's n over 3, canceling out the pi's, and then 2 over 6 is 1/3. So that's n over 3. And likewise, the second term, minus 3 cosine of 8 pi t, is periodic with period. And here, I won't use n again because this is a different function. I'll use m here. M 2 pi over 8 pi. Here's the 8 pi. So m 2 pi over 8 pi, which is m over 4. And so for our period, we want something that will be a period for both parts of this function. And so we want t to be equal to n over 3 in order that it will be a period for this. But we also want it to be equal to m over 4 so that it will be a period for this second part of the function. So we have t equals n over 3, which is also equal to m over 4. Now let's just look at the second part of this equation for a moment. So we have n over 3 equals m over 4. So if you cross multiply, you get 4n is equal to 3m, which says that m over n is equal to 4/3. Now obviously there are an infinite number of combinations of m and n that would satisfy that, but why not let's just pick the easy one, which is m equals 4 and n equals 3, okay? So I'm going to pick m equals 4 and n equals 3. Okay, well, I can plug in that if I plug in m equals 4, or if I plug in n equals 3. Either one, it'll give me t equals 1 equals 1. So either choice gives me t equals 1. So we're claiming that t equals 1 is a period of this function x of t. And I will check that. If it is indeed a period, then x of t plus 1 should be equal to x of t. So let's check and see. X of t plus 1 would be 2 sine of 6 pi times the quantity t plus 1 minus 3 cosine of 8 pi times the quantity of t plus 1. That becomes 2 sine of 6 pi t plus 6 pi minus 3 cosine of 8 pi t plus 8 pi, which is, of course, since the sine function itself is periodic, and it will, every time its argument increases by a multiple of 2 pi, it will repeat. And so 6 pi is a multiple of 2 pi, and likewise the same thing goes over here. 8 pi is a multiple of 2 pi. So this expression is just the same as 2 sine of 6 pi t. This expression is just the same as minus 3 cosine of 8 pi t. So we have this, which is our original function x of t. So we have shown that x of t plus 1 is equal to x of t, and therefore 1 is indeed a period of x of t. Now let's look at example 13.5. Let's express this function in terms of singularity functions. Now, I hope that you will try to do this yourselves first before looking at the answer. So I suggest you take a break, and then after you finish, let's come back to work together. Okay, so I hope that you were able to get this, but let me show you what I would do here. As I go from left to right, I see that I don't have any functions at all until I get to t equals 0, and then I have something that's ramping up here, and you can see since it goes from 0, 0 to 1, 1, it has a slope of 1. So this is r of t. But once I get to t equals 1, I want it to level out. So I have to subtract from it r of t minus 1. That will be a ramp down with slope negative 1, and so that will flatten out the curve. Then once we get to t equals 2, I want this to start sloping down. But notice that this slope is not as steep as this slope. In fact, let's see what this slope is. It goes down 1 unit. It has a vertical change of negative 1 over a horizontal change of 2. So the slope is negative 1/2 here. So I have a negative 1/2 r of t minus 2. This will make it start at t equals 2, and it starts going down with a slope of negative 1/2. But then when I get to t equals 4, I want it to flatten out. So that's why I then will have to add in a positive 1/2 r of t minus 4. So I claim that this right here is how to express that function in terms of singularity functions. And we can check this pretty easily. So let's look at this. Okay, we notice that this first term, as we're going, t is going from left to right, from negative infinity, and is going in the positive direction. All of these are off. None of these functions give any contribution as long as t is negative. But this function, the first one will turn on at t equals 0. The second one will turn on at t equals 1. The third one will turn on at t equals 2. And the last one will turn on at t equals 4. So let's see then what we get. When t is less than 0, all of them are 0. So we just get 0 if t is less than 0. Now once we get past 0, but we're still less than 1, then just this first one has turned on, and r of t is equal to t. So that's why we have this t here. Now, as t continues to increase and moves past 1, but is still less than 2, then that first term is still on. So we still have the t, but now this second will come in. So we have minus t minus 1. And then as we continue to increase t, and it gets past 2, but not up to 4 yet, then this term will also turn on. So now we still have the first term, so we still have t, we still have the second term, so we still have this minus t minus 1, but now we have a minus 1/2 t minus 2. And then finally, once t goes past 4, we have to include all 4 of these terms. So r of t gives us the t, minus r of t minus 1 gives us minus t minus 1, minus 1/2 r of t minus 2 gives us minus 1/2 times t minus 2, and finally the 1/2 r of t minus 4 gives us 1/2 t minus 4. And now if we simplify each one of those expressions, we get 0 for t less than 0, t for t between 0 and 1, 1 for t between 1 and 2, 2 minus 1/2 t for t between 2 and 4, and 0 for t greater than 4. If you compare that with the picture, you will see that that is exactly right. 0 for t less than 0, and also 0 for t greater than 4 is equal to t when we're between 0 and 1, and it's equal to 1 when we're between 1 and 2. And the only thing that's tricky is this the correct expression for the function when we're between 2 and 4? Well, let's see if it agrees. At t equals 2, that would give us 2 minus 1/2 of 2, or 2 minus 1, which is 1, 2, 1. Okay, that agrees. And at t equals 4, that would give us 2 minus 1/2 of 4, or 2 minus 2, which is 0. And indeed, at t equals 4, it goes to 0. So this does look like it's the correct expression. So therefore, what we have here, this expression right here, where we have expressed x of t in terms of singularity functions, is indeed correct. And final problem that I wanted to show you to just review is we look at example 13.6, and I've given you actually 5 different systems here, 5 different input-output equations, and ask you in each case which systems are linear, which means that they have the additivity. Let's see, let me stop here for just 1 second because I want to use exactly the same terminology we did before. So let me pause this. Yes, indeed. Different books use slightly different terminology, so I wanted to make sure of what we had, and I went back to lecture 6. But indeed, it is the additivity property and the scaling property. That's what we need to check to see if a system is linear. And then for time invariance, what we want to check is to see if when we have input x of t plus tau, does that give us output y of t plus tau? And so if we go down the list, the easiest thing to do, I think, in each case for checking linearity is it's real easy to check for additivity. I think that one's maybe even easier to check than the scaling property. So anyway, we see here that, if y1 is sine of x1 of t and y2 is equal to sine of x2 of t, well then if we have x1 plus x2, will that give us output y1 plus y2? And that's definitely not the case, because the sine of x1 plus x2 is not sine of x1 plus sine of x2. So this system is not linear. However, it is time invariant. If we replace the t in here by t plus tau and the t in here by t plus tau, and then evaluate at various values of t, we will recover the same kind of equations that we had here. They will be for different values of t, but we will recover the same equations. So this is time invariant, but it is not linear. On the other hand, this second example here, where we have y of t is equal to sine t x of t, this is similar to an example we had, and this one is linear, but it is not time invariant. And the reason it's not time invariant is because of this term right here. If we didn't have this sine t out there, this system would be both linear and time invariant. But the presence of this sine t term takes away the time invariance. Okay, moving to the next one, x squared of t. And I think it's pretty easy to see that that one is not going to be linear, because, you know, if y1 is equal to x1 squared and y2 is equal to x2 squared, then you check and you say, well, is y1 plus y2 equal to x1 plus x2 quantity squared? And unfortunately, that's not true. There's a cross term. We do indeed, if we had x1 plus x2 here, we would get an x1 squared plus x2 squared, but we'd also have a middle term, a cross term of 2x1, x2. So this system is not linear, but it is time invariant. And finally, for D and E, both of these systems are both linear and time invariant. Now, I think that it's easy to see that for D, and I think it's easy even to see on E that this system is linear. But how do we see that it's time invariant? Because remember, what we did to check for time invariance was we would start with our original equation, and we would check it for a few values of t, and then after shifting the t to t plus tau everywhere in the argument of y and in the argument of x, we would see if we get the same equations. Well, this one's a little tricky because the t over here doesn't appear to be in the argument of x. So I want to show you how you can handle something like that. So for this case E, note that y of t, okay, here's the equation for y of t, but let's let u equal tau minus t. Now, if we do that, du is equal to d tau. That's not a mystery. But then, if we make that substitution, okay, the y of t on the left-hand side remains the same, but on the right-hand side, when we change to the dummy variable u, since u is equal to tau minus t, the upper limit becomes t plus 3 minus t, so the upper limit becomes 3. And similarly, the lower limit, when tau is equal to t minus 1, u will be t minus 1 minus t, or just minus 1. So we now have integral minus 1 to 3, and what about this tau? Well, if u is equal to tau minus t, then tau is equal to u plus t. So we have the u plus t here. So y of t can be written as the integral from -1 to 3 of x of u plus t du, and now we do have t explicitly in the argument of x. And so now when we replace t in both the argument of y and in the argument of x by t plus capital T, or t plus tau, whatever you want to call it, when we do that, we will get this, and then we can check and see. Now we have the equation written like this. We can check at t equals 0, we would get this. At t equals 1, we get this equation, and at t equals 2, we get this. But if we check this altered equation, at t equals negative t, we would get this, which of course is identical to that. At t equals 1 minus t, we would get this, which is identical to that. And finally, at t equals 2 minus t, we would get this, which is identical to that. So that tells us that indeed, as we said already, E is time invariant. So that one was just a little trickier there to see how to get that t. I mean, it's not so obvious here that this t is still, in a sense, inside the argument of x. Okay, well, then that concludes our this bit of review. And once again, I want to stress that this is not comprehensive. This is we haven't reviewed here any of our more recent material, and in fact, we didn't cover every single thing from earlier either. But I do think that, or hope that, or think and hope that this will be useful review for you as you prepare for the midterm exam. So that concludes lecture 13, and thanks very much.